Here is the power spectrum of that map. Well, actually, it's not. It's the power spectrum of the two previous generations produced by Halley, 2013 and 2015. So what you're seeing is the raw power spectrum C for the lensing potential, actually, with factors that basically amount to 4 powers of wave number outside. So that is so as I told you that there's a Poisson equation, del squared lensing potential is twice kappa. That says minus k squared minus psi is twice kappa. So if you square that, you get a k to the 4th. So actually, we are seeing a power spectrum of the kappa field, even though it's presented as a power spectrum of the lensing potential. What you can see is that the 2015 results are significantly more precise in terms of their error bars than the 2013 ones. I explained yesterday that's because in 2015 the information from the polarization of the Planck CMB map was added to the reconstruction, whereas the 2013 one was based on temperature data only. One thing which I'll say a bit more about shortly is that this isn't the power spectrum of the raw map, because at multiples of, say, 1,000, where the signal seems to be very small, the actual power in the observed map is huge. And that's because, as I explained, the reconstruction is noisy. It depends on the small-scale instrumental noise and the limitations of the finite Planck beam. So that noise contribution has had to be subtracted to leave an estimate of the residual signal, which is barely detected really beyond wave numbers of 500 to 1,000. But it's wave numbers of around about 100, it's detected with high signal to noise, and there's a solid line here which represents not a fit, but a prediction. So this is taking the cosmological parameters derived from the primary temperature map, the headline Planck analysis, and just predicting what the lensing power spectrum should be. And as you see, it's really beautifully consistent in shape and in amplitude. So bear that in mind, because that's a really important cosmological constraint. I can show you the latest thing on this, which is from the 2022 map, where the extra data and the reanalysis, this is the so-called PR4 release by Julian Karen et al., and you can see the error bars have tightened still further. So, if you want to understand what cosmological constraint this good agreement produces, you can ask, well, if I change the cosmological parameters so that the black line becomes a poorer fit to the data, what quantity is it that one's actually measuring? And I'll tell you the answer now, and try to justify it in a little more detail shortly, but here it is. To a good approximation, the amplitude of CMB lensing allows you to read off this combination of cosmological parameters, the 1/4 power of the density parameter times sigma 8. Right. I hope that everybody's heard of sigma 8. Just let me remind you that what it consists of is taking a fluctuating density field, involving it with a sphere of radius 8, connection minus 1 megaparsecs, and then getting the RMS of that smoothed density fluctuation, and that's the thing we call sigma 8. So it's a historical and not ideal measure that gives us the normalization of the power spectrum. And we know that combination, so we know this normalization to a small correction depending on the density of the universe to better than 3% from the lensing data. But this is amazingly precise already, even though, as we saw, the bank reconstruction is quite heavily limited in some ways. Okay, well so bear this combination in mind, because that will reappear later in what I have to say. All right, so a few more words about the noise. In the trade, what we've done for making this reconstruction of the CMB map, which is, let's go back to the equation. Oh, there it is. You can see that the quantity that we dealt with, remember, it's the divergence of the temperature times the gradient of the temperature, albeit with suitable smoothing of the temperature. So that's quadratic in the basic temperature map. And so it comes under a class of things that statistically are called, guess what, quadratic estimators. And these are valued in cosmology because they're relatively simple in their statistical properties. And it's worth bearing in mind that, in principle, things don't have to be this easy. So this distinction was first pointed out as a really classic paper by Max Tegmark, where he said, what should you really do if you have a map of the sky in microwave background or some other quantity, and you wanted to estimate its power spectrum? Well, here's the process. First of all, I should emphasize that normally, with the microwave background, we assume that the primary temperature fluctuations are Gaussian. So what that means formally is if you take the actual map data, so I want you to imagine that you have a two-dimensional picture of the sky, take all those pixels, stretch it out into a single one-dimensional data array, so call that vector D for data. The joint statistical distribution of all those values, of all the pixels, is a Gaussian. That is, it depends just on the quadratic form that you get from the inverse of the covariance matrix. So you need to know the covariance matrix of pixel here with pixel here for all possible pixel combinations. That can be predicted from the power spectrum. So for a Gaussian field, it's a very statistically economical process. If you write down the power spectrum, you can calculate, as I explained yesterday, a correlation function for the field you're looking at. And then you have the full statistical distribution. So what you really should do to estimate the power spectrum from the data is to say, well, the power spectrum injects itself into the calculation of the covariance matrix. And so you use this probability distribution as a likelihood function. So you fix the data and you vary the parameters in the power spectrum to maximize this likelihood. That's the formally correct thing to do if the field you're dealing with is Gaussian, as the microwave background is assumed to be. But as you can see, that's an extremely non-linear combination of the data. So to calculate any other properties about the power estimator that you produce, for example, it's you have to know the uncertainty in that estimator. That's quite complicated to do, and that's why if you have a simpler estimator of the power that goes directly quadratically from the data, that is to be preferred. Now that's not what we have quite here. So schematically, our estimate of the lensing potential is quadratic in the temperature. So what that shows you is if you take the power spectrum of the lensing map, that's now something that's schematically fourth order in the temperature. So this now is interesting, because if you want to calculate the noise on, if you want to calculate the power spectrum of the map would be biased, because even if there was no lensing, because the map is noisy, you're still going to get some fluctuations in the apparent lensing potential. And so if you can't take the power spectrum of that, you'll get something non-zero. So this is a noise bias that needs to be subtracted off. But viewed from this point of view, you can see that actually, to subtract it, you need to know what's called the 4-point correlation function of the temperature. Now, if the temperature field, the primary CMB fluctuations are a Gaussian field in the same sense here, then that 4-point function splits up into products of 2-point functions, and it can be calculated. This is just like saying, for a single 1-point probability distribution function, if you have some Gaussian distributed quantity with an RMS sigma, then what is the fourth power? Answer is sigma squared times 3. So the fourth moment is predictable if you know the second moment. But you have to assume that things are Gaussian. So the basic ability to make a map is only dependent on this general idea of translational invariance, that the 2-point function in Fourier space was a delta function. That's all we needed to assume. It would work whether the microwave sky was Gaussian or not. But to estimate the noise of it, we have to assume that the CMB is Gaussian. Okay, so it's only at this stage that that additional assumption becomes critical. And this is roughly what it looks like. This is the black line is the underlying prediction, and the red line is this Gaussian noise term. So you can see it crosses over at LF 100-ish, and it's of comparable magnitude to the actual signal, even at the peak. And LF 1000, of course, it's hugely dominant. So it's really impressive that we can measure something up here and subtract it well enough to reveal this small residual. All right, so you should have been wondering, there's this beautiful theory line that goes through the data so nicely. How could I predict that? Where does that curve come from? How do we get it? So I just need to say a few brief things about that. So let me remind you first of all what it is that we're making a map of. It's the convergence, or I'm sure that the convergence is simpler to understand. So here it is, kappa. It is basically in the form of a line integral of the density times some kernel. And this kernel contains two things. First of all, it's proportional to the total density. That's important, right? Because lensing is produced by density fluctuations. So delta is the fractional density fluctuation, but we need to multiply by the total density to see the actual fluctuations in mass. And then there are various distance dependent factors that just allow for the geometry of the gravitational lensing. So, a lot of things that one might think about observing of this general form. Some observable is a line of sight integral of the density field with some radially dependent weighting. So, for example, you could ask, give me the number density of galaxies on the sky as a function of position. That also is exactly of this form. Just the kernel will tell you something about the probability distribution of the redshifts of those galaxies. So you can ask a general question about the correlations in 2 dimensions on the sky of such projected things, knowing something about the 3-dimensional correlations of the field that you're projecting. And the general solution to this was given us so much in cosmology by Jim Peebles many years ago. I attempted to write one. I was attempted to derive this, but here is his expression for the cross power spectrum. So maybe I should explain what that is. Alright, so I have a field. It's the sum of Fourier modes times waves, and we have the power, or in 2 dimensions, write it as C, So if I have the same thing, but for two different fields, the cross power is just the product of the Fourier amplitudes with a complex conjugate. It's just an obvious generalization. But this is something. Oh God. They really need to put the laser button in a different place on this thing. It's too close to the page up and page down. All right, so here is the cross power for two projected quantities of this form. It involves three integrals. One is an integral over wave number, and this thing is the dimensionless power. Remember, this is d variance in delta by d log k. You have whatever the kernels for your two fields are, and these things are spherical Bessel functions. So when you go to the awful thing about this expression, that it's exact, is that first of all it's a triple integral, so it's slow. Secondly, when you go to high wave numbers, you need Bessel functions of very high order. So they oscillate very rapidly, so that's also numerically inconvenient. So it's worth knowing that this thing exists, but for most purposes it's not used. What is used is an approximation that's valid for small angular scales, which for CMB Lensing is actually most defined. And this is a thing called either the Limber approximation, or I prefer to call it the Limber-Kaiser approximation, as I'll explain. So I don't know if you've come across this before. This is a really cute argument. So just let's say we want to know the correlation on the sky of our two projected quantities A and B. Well, that's just, each one is a projection of delta times a kernel, so you multiply them together, you get two deltas, two kernels, and two radial integrals. You want to ensemble average that to get a correlation function. So you're going to ensemble average this and produce the correlation function in 3 dimensions. Now comes the approximation. For most things to do with large-scale structure, the correlation function is only significantly non-zero out to relatively small distances, say 100 megaparsecs or so. Whereas the depth that one's integrating over, say, going back to large-scale structure, to large scattering with a microwave background, is 10 gigaparsecs. Okay, so the projection is very long compared to the coherence length of galaxy clustering. So to a good approximation, R1 and R2 have to be pretty close to each other, otherwise there'll be no clustering signal. And therefore you just set them identical, and then you have an integral over the correlation function where the limits can just be taken going to plus or minus infinity. So x is now some small radial distance coordinate, r theta is the transverse separation. Is that clear? And all we're doing is saying I'm standing here, I have a pair of galaxies, they have some transverse separation, some radial separation, and some transverse separation, where theta is the angle of subtend. And if you Fourier okay, so this equation here is Limber's equation going right back to 1954. And it's a two-dimensional integral, so that's progress. Peacock's general expression is three-dimensional, three integrals. But what Kaiser showed in 1992 was that if you Fourier transform this expression to obtain the angular cross spectrum, you actually reduce that to a single integral. And it's just basically a blurring, depending on the kernels of the projectors of the three-dimensional power spectrum. So that's a really cute and numerically very fast and robust expression, which is what's used in this literature. All right, so let's just go back. So we can predict the angular power spectrum knowing the kernel for lensing, which we do. It depends on cosmological parameters in three ways. Once it's got this overall density scaling outside, once because it's got the density field inside, and although I haven't written it explicitly, delta is a function of radius in two distinct ways. I mean, first of all, as we move through space, density fluctuates, that's fine, but at large distances, we're also looking back to earlier times in the universe. So you're sensitive to also the change in amplitude of the density fluctuations with time. They were small in the past, gravitational instability makes them grow in a predictable way to the present. And thirdly, cosmological parameters, again the density parameter, dictate the relation between these distances and redshift. So there's three factors that make the predicted power spectrum of kappa cosmologically sensitive. All right, so we're going to be using this final Kaiser-Limber equation, and that's where the prediction for the CMB power spectrum comes from. So let's look at the theory results in a bit more detail. So at the top, what I'm showing you is the standard model prediction for the kernel that goes into the projection. So this is a function of redshift 1 here, redshift 10 there. So you can see that the kernel actually peaks at a redshift of around about 2. So it's a kind of crossover. Obviously, the universe was more uniform at redshift 2 than it is today, but the strength of gravitational lensing increases with distance. And so those two effects combine to have a maximum efficiency at redshift 2. And so now you can take that kernel and do the integration to predict the power spectrum. And that is this top line here, peaking at a wave number of about 100 and then falling. But what this extra curve shows is how that builds up with redshift. So each of these coloured bands shows you integrating the signal that lies within some redshift. So by the time you get to redshift 20, basically you've got it all. Redshift 2, you've got 3/4 of the signal. Redshift 0.5, well, it depends on, the interesting thing is it depends on the wave number. That's wave numbers above 100, there's very little signal coming from redshifts below 0.5. But as you go down to, say, maybe 50 or 30, a significant fraction of the signal still comes at these rather low redshifts. Okay, so this is kind of tantalizing, because what we've shown is that the overall data agree very well with this total sum curve. But what we would like to do is to be able to dissect the contributions to the CMB lensing of these different redshifts and test the theory, because that gives you a direct measure of something that's very important, which is the rate of growth of density fluctuations. And this is considered to be interesting. Well, if you make the cosmological model non-standard, so standard cosmological model includes a cosmological constant, that is a vacuum density that's independent of time. A more general dark energy approach would say possibly that density could evolve slowly. if that happens, that changes the rate at which density fluctuations grow. It's also possible that we have the wrong classical theory of gravity, it's not Einstein's relativistic theory, and then that would also manifest itself in a different rate of growth of fluctuations. So the growth rate of fluctuations is seen as really important to pin it down, either for measuring the properties of dark energy or for testing gravity. The trouble is, apparently we can't do it because we only have data. The CMB reconstruction measures dark matter wherever it is, but there's no redshift information. Well, there is a way of doing this, which I'll be getting to shortly, but just before I tell you how to solve that puzzle, I want to say a few words about where this is headed. I've emphasised that how well this reconstruction works depends, first of all, on the resolution, and secondly on the noise. So with Planck, the beam is pretty big, given the kind of arc-minute length deviations, and on those scales it's dominated by instrumental noise. But future experiments won't have these problems. They will have beams that are significantly smaller than 1 arc-minute, and basically at their resolution they'll be completely signal dominated. There's a range of these. Ones operating now are ACT, the Atacama Cosmology Telescope in Chile, SPT, telescope at the South Pole. These will soon be superseded by the Simons Observatory, which will also operate in Chile, and in about a decade the US is congealing to a massive effort called, not a very imaginative name, CMB S4, Stage 4. It's just all the independent micro background groups that will pool their resources into a single massive instrument. But even what's coming down the line, which the soonest will be results from ACT, are going to be phenomenal. And I'm going to give you a little preview of that, and these are slides that I've borrowed from a talk given by Frank Chu, pronunciation. This is a meeting in Cambridge last month, and I was really excited to see this. So here is a slice of the sky. This is real data, not simulation. On the right is Planck, on the left is ACT. And you can see by eye just how much better the noise performance is. And you can also see that the resolution is superior, but it's the lower noise that stands out. And it changes everything. So here's the Lensing power spectrum. Here is the current noise, the Gaussian noise bias that comes from the Planck map. You're barely being beaten by the signal right at the peak. ACT will reduce that by an order of magnitude at the large scales, and therefore the wave number at which the map becomes signal dominated now changes from a couple of hundred to several hundred. So we get finer detail on the map, many more modes measured in the linear regime, and the precision will go up hugely. Remember, the Planck data are already measuring this overall measure of normalization to 3%. So we're going to get an order of magnitude improvement from ACT. And so suddenly it's going to be the most powerful cosmological probe on the planet for some purposes. That is completely going to eclipse the results from gravitational lensing of galaxies. So this is the next big thing on the block. This is why I was really motivated to come here and talk about it in detail. And it's due by the end of this year, they promise. There will be papers out on the archive, and you really should look out for this, because it's going to be phenomenal. And I can even show you what it looks like. So this is the ACT map. You can see what fraction of the sky it covers, smaller than Planck, but still 18,000 square degrees. And everything that you're seeing on this map, these fine details, aren't noise. These are basically real signal. And you can convince yourself of that if you blow up a little patch and you superimpose the lensing reconstruction, which is in colour, white, the high density black for low density, and put on top of it contours which are the far infrared background. So this is the projected density on the sky of high redshift galaxies seen in the far infrared. So we don't know exactly what their redshifts are, but we know that they're comparable to the redshifts of order unity where the CMB signal peaks. And there's a spectacular degree of agreement. So almost every little peak in this map is matching a peak in the right distribution. So everything here is real. It's a complete qualitative change in precision. So when this comes out, it's just going to be amazing. I can't wait. All right, so now I'm going to tell you about how we solve this problem of extracting the redshift-dependent lensing signal. Any questions on what I've just said so far?
I have one. So the slide you showed before, the last one, was a simulation of the real data from up?
No, that is the real data.
So it's real? Like
Yeah, that's the actual universe.
Thank you.
Question?
Yeah.
Yeah, maybe when you were showing the like how lensing was increasing the signal depending on redshift, you show with the results now we can see like up to like redshift 2, right?
Yes.
So
Well, beyond.
yeah.
Okay, because you can see going from even redshift 10 to 20 increases the signal by, what, I don't know, 5%.
Yeah.
So that 5% difference will be very easily detectable with the new data.
Okay.
Okay, so it really matters what's going on with those redshifts. And as you can see, actually, there's some, God. In the kernel, you can see there's some sensitivity even to structure at redshift 100. Here, by the way, is the microwave background itself, right? So it shows how much of the space between us and the CMB, the lensing probe actually manages to cover. So, there's a lot of talk and a great deal of excitement about probing structure in the dark ages with the 21 centimeter observations, which can take us out of this regime, but lensing actually gets beyond that in principle.
And would that get better with the new data, like the?
Well, yes and no. I mean, the problem is you measure the total very precisely now, but how do you split it up into its different redshift contributions? So that's the thing we're talking about right now.
Okay, better.
Thank you. So, do you expect here that the more bigger influence for lensing it is really small redshift, if we speak about CMB, near the Z equal 10, yeah?
Well, as I said, there is a contribution at redshift 10, but it's what's this, 5? Okay, so going from redshift 5 to redshift 10 increases the signal by, I don't know what, 5% or so?
So, can we use new data from James Webb Space Telescope, which we expect for example, restore matter distribution at this redshift and take into account how big influence we have for CMB lensing. Compare with observable data, I mean.
Well, you obviously the CMB Lensing signal knows about a combination of things that are happening at all these different redshifts.
Yeah.
So it's redshift 10, redshift 1, redshift 0.5, it's the same issue. How do you split this signal up into its contributions from different redshifts and check that they're all matching the theory or not? So that's the problem I'm now going to solve.
Okay, thank you.
Okay, and the way this is done is called tomography. Tomography is just a medical word for chopping things up. You know, you put in a scanner and you take X-ray slices of your head, and that's tomography. Okay, and I'll just show you this. So the way that we can extract the redshift dependence of the background signal then is by cross-correlation with catalogues of objects where we do know redshifts. So if we have galaxy catalogues, so we have a distribution of a fluctuating density on the sky that we know comes from galaxies in a particular redshift slice, then the degree to which those number fluctuations correlate with the lensing map tells us the fraction of the lensing signal that comes from that redshift slice. That's the basic idea. And what I'm going to do is show you one particular study that does exactly that, which was carried out, it was a paper in 2020, led by my PhD student, Alan Hang. The data that we exploited for this come from actually the other thing in cosmology, apart from ACT lensing, which is also published as a very exciting point. And this is the DESI experiment, the Dark Energy Spectroscopic Instrument. So this is a slight digression, but I think you'll find it interesting because this is really changing very fast. What this project has done is taken over the 4-meter telescope at Kitt Peak, which, by the way, was very nearly destroyed just a month or so ago in a big fire. So it was only just saved by heroic action by the fire brigades on Kitt Peak. What this does is stick a spectrograph at prime focus that robotically can position 5,000 fiber optics. So over a 3-degree field, it will get 5,000 redshifts in a single exposure to the sky. And it's going to give us over the next 5 years, it's already been going for about 1 year, so next year there'll be a big pulse of papers based on that first year of data. After 5 years there'll be something like 30 million galaxies, so that's 10 times the volume of spectroscopic data that currently exists. And there'll be various subsets, including so-called bright galaxies that go to redshift 0.5. It's just a magnitude limited sample, but then various special categories of reds, emission line emitting galaxies, and even quasars that will span the range right out to redshift 3. So it'll be an extremely comprehensive spectroscopic probe of the universe. Here's what some of the hardware looks like. The fiber optic positioners are things about the size of my little finger. So you put a fiber optic at the end, and it has piezoelectric motors that enable that to rotate, so that it occupies some small patrol area on the sky, and you just put all these things in this preformed support with holes for each positioner. There's a number of these petals that make the complete focal plane. There it is with a human hand to give you an idea of the scale. And there's one petal filled up with all its positions. So it's a colossal piece of hardware. I couldn't resist showing you this, which looks like a simulation, but it is actually not. This is the sky distribution of real galaxies. I'm contrasting here a historic image now. This is the 2-degree field galaxy redshift survey, which was a revolutionary leap in the size of spectroscopic surveys using also fiber optic spectroscopic technology 20 years ago now. So this gave us 250,000 galaxies, which seemed a lot at the time, going out to about redshift of this is redshift 0.25. So this is a small slice. I mean, these are slices that are on the sky, strips that are just 2 degrees wide. So this is part of the DESI Bright Galaxy Survey, going out to redshift 0.5. And luminous galaxies and quasars will take it out further. I'm not showing those. So we're going to have many such slices. So suddenly it's a colossal expansion in the volume of data. And this, again, looks like a simulation, but this is the real universe. It's very exciting times to have this coming into focus. Now, you can't do a spectroscopic survey like DESI unless you have a knowledge in advance of where the galaxies are. So one of the things that DESI had to do is to carry out a complete deep photometric survey of the areas of sky of interest. So mostly in the northern hemisphere, going into the south a little bit, 17,000 square degrees on the whole. So pretty impressive depths in GR and Z photometry. Certainly this is a couple of magnitudes deeper than the Sloan survey, so it's the best existing uniform CCD photometry over much of the extragalactic sky. And it's all public, so there's a website I encourage you to go to, legacysurvey.org, where you'll find the DESI Legacy Survey, and you can just browse the sky. So here, for example, there's the quasar 3C273 with its jet. You could lose yourself in it for hours. Well, it's only 3 wavebands, GR and Z, but you can supplement the data set by a completely different experiment, which is WISE. So WISE was a phenomenally successful satellite. It was launched in 2009. Its initial mission was 2 years, but it was revised, intended taking data up to 2018. And this gives you an all-sky survey. It's, well, for our present purposes, the particularly interesting waveband is the 3 micron one. So it's actually it's the same waveband as a lot of the most exciting recent JWST data. It's a much smaller telescope with inferior widespread function. But as a statistical engine, it's really been revolutionary. So what the object selection for DESI has done is combine the 3-band optical imaging with the infrared data from WISE. What it allows you to do is to estimate photometric redshifts pretty accurately. So you've probably heard about photometric redshifts. The idea is that galaxy spectra contain characteristic features, depending on the galaxy type. If it's an old stellar population, so luminous red galaxies have a strong break in the spectrum at around 4,000 angstroms, and so depending on the redshift, that sits in a different filter and changes the colours of the galaxies in a way that allows you to have an estimate of what the redshift is. And so this really works. So the way we do this, and there's a lot of algorithms for estimating photometric redshifts based on this photometric information. Many current algorithms use some form of machine learning, which, not that it's a bad thing, but I prefer, if possible, to have a simpler method that one has more control over. So what we did was simply the most empirical thing possible, which is to take a cube in color space, G minus R, R minus Z, Z minus W1, and try to find in external data sets of known spectroscopic redshift objects of similar colors in those 3 dimensions, and use that to calibrate that particular color combination in terms of spectroscopic redshifts. Some regions of color space don't have a good spectroscopic calibration, but the nice thing is that you can then just exclude them, so you make an object selection that's confined to objects where you can estimate the redshift well, which is possible for about 80%. And it gives you redshifts with a fractional precision of not much worse than 1%. So his spectroscopic redshift is the photometric estimate. It's a log scaling of number, so it's really very tight. This, it's really important to get this right, I have to say. It's a similar problem as probably Hank Hoekstra told you in galaxy shear. So if you take redshifts of those precisions, and you can chop the sample up so that the DESI data probe out to about a redshift of 0.8. So somewhat arbitrarily, we took things into 4 tomographic bins. You can see the bins here up to 0.3, 0.45, 0.6, 0.8. And the curved lines are a best estimate of what the distribution of tune redshifts corresponding to that photometric selection is. So it's very important to know what those curves are accurately. So you have to understand the calibration of the photometric redshifts, because this is what goes into the kernel to predict the cross correlation. So here's what sky maps of those things look like. So this is the factor redshift 0.3, 0.45, 0.5, 0.8. And if I didn't tell you which was which, you could tell. You can see that this one is further away than this one, because the large scale structure is quite close in front of your face, and you take it further away, it tends a smaller angle. So all the structure you can see in here is really all high signal to noise. And so the interesting thing is, how do each of these maps correlate with the CMB lensing? Because the degree of that correlation just pulls off, as I said, the fraction of the CMB signal that comes from each of these bands, which is what we needed. Okay, so this plot shows you, I said high signal to noise, so this is the galaxy auto spectrum. That's the blue data. There's a solid line that you can see here, which is the prediction. Oh, okay, so here's the key equation from the Kaiser-Limner formulas that I gave you. We're basically integrating over the power times some kernel that depends on the redshift-dependent, the distribution of redshifts. What do you put in here for the matter power spectrum? You can calculate that according to linear perturbation theory, which gives you this solid line. So you can see from wave numbers of about 500 and up, nonlinear corrections are important. We touched on this yesterday. We said that baryonic effects. First of all, we expect small-scale power to be larger than linear theory, simply through nonlinear collapse left out by the structure. But in detail, this nonlinear enhancement depends on whether the baryons and the dark matter have separated or not. So to get this really precise is quite hard. But these corrections are only important at wave numbers above about 500, leaving a beautiful, clean, linear probe below that. And this is the regime in which we measure the CMB lensing most accurately. Another thing to point out is that we are interested in P being the power spectrum of matter fluctuations, but galaxies are not direct traces of the dark matter. Their clustering amplitude is biased by some amount, which in principle one could try and estimate, but can be regarded just as an empirical parameter. So the bias parameter B, or it's B squared in the power. So the galaxy auto power is measurable, so we can measure the combination B squared times the amplitude of the power, which is proportional, as I told you, to this normalization sigma rect. So what you would say is that CGG applies some knowledge of that combination. All right, now here is the cross power. Okay. Again, so for the 4 different bins, solid line is the standard model, standard Planck cosmology prediction, and blue is the measurements. So it's not as precise as the galaxy orbital power because the lensing map is noisy. But it's impressive that you get a good detection. And at first sight, everything looks pretty good. But if you look more closely, you'll see that the blue points tend to lie below the black line. And if you just give yourself a nuisance parameter and say, I'm going to scale this black line up or down by some factor A, and try to determine the best fitting amplitude, the answer is you get an amplitude that's 10% low compared to Planck. And that's significant. It's like a 4 sigma deviation. All right, so that's a couple of slides about the details of that, and I'll skip over it for now and go back and ask questions. So what would a low signal for these cross correlations, pulling out the low redshift part of the CMB lensing signal mean? Again, let's write down the equation for the cross power. There it is. We need to know 1 power in the bias because we're cross-correlating biased galaxies with kappa times the power times the lensing kernel times the redshift distribution of the galaxies. And the lensing kernel is proportional, as I've emphasized several times, to the overall density of dark matter. The bias disappears because, so this combination will be proportional to B sigma 8 squared, but we know B sigma 8. So overall, this combination just has an unknown scaling with 1 power of sigma 8. So this expression shows you that the main scaling of the cross power should be linearly proportional to the matter density, linearly proportional to sigma 8. That's not quite true, because extra nonlinearities creep in because this integral extends to higher redshifts, and then the kernel the distances are also density dependent. But actually, omega to about 0.78 is a good approximation to the scaling of this cross power. So you can say that therefore, the measurement of the cross power amplitude relative to Planck gives you a constraint on that combination. So the low redshift CMB lensing tells us the combination omega matter to 0.78 times sigma 8, and it's about 0.3. So I was very pleased with that result. Because it reminds you of something else in the gravitational lensing world. Did Heck show this picture? The lensing banana? Did you take out the lensing banana? Okay, so weak gravitational shear operates in a very similar way. Except it doesn't probe to as high redshifts as the microwave background. And so the amplitude of the signal there scales according to a parameter that in the galaxy world is called S8. And it's sigma 8 scaled as a 0.5 power as the density parameter. So they have a locus which, well, there's different experiments on here, but they are largely consistent with this sort of banana, with a an S8 value of about 0.77, and offset from where the Planck temperature parameters would prefer it to be. And so this is one of the infamous cosmology tensions that people talk a lot about. And it's been around for a long time, actually. The first measurements indicating a low number for this go back to 2007. And so it's always been 0.7 something, as long as people have been trying to measure gravitational lensing distortions of galaxy shapes. And at the moment, it's offset in terms of the amplitude of this, the location of this banana by about 10% compared to Planck. So that should sound interesting, because I showed you that the low redshift contribution of CMB lensing was also apparently 10% lower compared to Planck. So something weird going on at low redshifts. Well, maybe and maybe not. You see, what should have been ringing alarm bells to you is that earlier on I've been saying how beautifully the overall CMB lensing signal agreed with the standard Planck prediction. And yet the low redshift part, and that was this combination omega matter to the 0.25 times sigma 8, gives that number. And yet the low redshift contribution of that signal is 10% low. Is that inconsistency? Because it's both the same CMB lensing map. Well, no, because these different signals have different density dependencies, and we can show them on a single plot. So the yellow band is this one here. It's the amplitude of the total lensing signal, and as you can see, it's really nicely consistent with the Planck prediction. The purple one is the weak galaxy lensing banana, the S8 one, which lies below. The red one is the one that I showed you from the tomographic study of CMB lensing. And actually, all of those lensing results are consistent, and they prefer a region of parameter space over here. So basically, you don't want to lower the Planck normalization, but there's a consistent preference for a lower density. So Planck, its fiducial density parameter is 0.315. All the lensing results want something that's actually significantly below 0.3. And if the universe has that lower density, then in fact everything that gravitational lensing has given us makes a consistent picture. And you can wonder what to do about this. You can either say that something is completely wrong, there's some error in the data, there's some new ingredient in the cosmological model, or it can be bad luck with statistics. And I'll be saying more about those possibilities after coffee. Let's just point out for now, though, that if you take a kind of formal combination, the least bad point from the point of view of both these experiments is this cross with a 95% contour, which is what we're seeing here, just touch, which is not really statistically very satisfactory to have that degree of disagreement. But on the other hand, if you say these are the cosmological parameters at that point, both Planck and lensing are consistent with that at 95%, so the disagreement is not colossal. Good. I think I will stop there, because we can now go on to the general question of these tensions. But let's leave that for up to coffee. We can have questions now if there's any remaining.
Peacock. What do you think could be the possible sources for the sigma tension?
I'll tell you that after coffee.
Thank you.
Thank you. I thought about cross correlation with galaxies catalogs, but when we do this cross correlation, we obtain only relations with baryonic matter distribution. Yes.
Well,
We estimated only a baryonic matter distribution in our universe, but we didn't know anything about dark matter distribution, but it also can some influence the lensing, yes?
yes, but that's all encapsulated in this relation here. That is the power spectrum of the galaxy distribution, which is what we measure, which is part of the baryon component, although not all, right? In fact, mostly it's not. Galaxies we detect because they contain stars. Stars are only 2% of the baryons of the universe. All the rest is in gas. Okay, so it's a small subset of the baryons that we're looking at. We know ample lines of evidence that galaxies are strongly associated with halos of dark matter. So there's some statistical association between the two. How strong that association is expressed by the amplitude of the bias parameter. So you're certainly not assuming that galaxies, that if you have a region of space where there's twice as many galaxies as on average, you certainly don't assume that that's twice as much dark matter as average. But where there's more galaxies, there's more dark matter for sure. How much more is expressed in this unknown bias parameter. But the point is, you have the amplitude of the galaxy autocorrelations and the amplitude of the galaxy CMB cross correlations. And so those two pieces of information allow you to eliminate that unknown bias.
Okay, thank you.
I had one small question, like this CMB lensing pattern which we are seeing right now, this is from the photons which are traveling from like pretty far behind. But do like other sources affect this lensing pattern? Let's say like there's a strong stochastic gravitational waves at the beginning. Will the pattern look different? Because right now the stochastic, they are small, so I don't consider them baby noise. But at the very beginning,
I mean, obviously, strong gravitational wave background influences the primary temperature fluctuations. So, if you think about what the CMB spectrum looks like, with zero gravitational waves, if there were primordial gravitational waves at some amplitude, that adds an additional component that rolls away at roughly L of a few hundred, where the main peak is. So there's some unknown amplitude of those waves. So we can be sure, because the spectrum doesn't do this, that the amplitude of those waves isn't too large. So if they exist at some level that can't be detected in primary temperature fluctuations, then there's any effect on the propagation of the CMB to us is going to be higher order.
Sorry, maybe it can be a question, but can gravitational wave from a supermassive black hole collision in an early universe, and now and gravitational waves from neutron star collision and star mass black hole collision, can we have some influence for this theory of lensing? Because all of that part of gravitational wave distort our space-time.
I mean, yes. So gravitational waves generated in the very early universe have this particular pattern, and they consist of a stochastic background and this random phase superposition of waves. But by the central limit theorem, gravitational radiation from a large number of neutron star binary mergers, this room is filled with a background of gravitational radiation from such things. So it's not a single chirp, but it's just a mass superposition of small signals. So in a way, the primordial gravitational waves and later astrophysical generation just combines into a single effective noise background.
I'm asked not about primordial gravitational waves, I'm asked about
yes, astrophysically generated ones
yeah.
more recently. But the point is, in the end, it's only the total amplitude that matters. It doesn't matter what generates them. Any gravitational radiation will have an impact on the microwave background. So
Okay.
we're pretty sure that the amplitude isn't so large. It's not the best constraint. Things like pulsar timing fluctuations limit the amplitude of local gravitational waves pretty severely.
Thank you.
How big is the effect of the Sunyaev-Zeldovich effect on discerning whether we see a gravitational lensing signal versus a fluctuation due to inverse scattering?
Well, as I said at the start, the SZ effect is a small scale phenomenon. So if you take a calculation of pure CMB fluctuations and then you superimpose these additional foregrounds, yeah, it's actually interesting maybe to blow this up. So let's have a look at, so this peak is at L equals 220. But let's focus on a region shall we say 500 to 1,000 or so. So the pure CMB might look something like that. The impact of gravitational lensing is interesting. Yeah, this gives you an idea. If you look at the lensed and unlensed, let's take a little patch. Focus your eyes on that. The main difference you see between lensed and unlensed is that little patch just gets expanded, right? So you can think of the effect on the microwave sky as sort of taking many copies of this. Some get demagnified and others get magnified. Yeah? And then you superimpose them all. So the effect of that is to smooth the power spectrum very slightly. So the impact of lensing would be to just broaden out. things like that. Okay, so even at wave numbers of 500 or so, there's an effect even in the power spectrum. On the other hand, if you ask what the SZ signal looks like, then it's something that starts to become important at L's above about 1,000, because this is very small scale thing. So I don't have a map to hand, but if this was real data, as I said, you would see just individual sharp dots on it from the SZ effect of rich clusters. So really, it's eventually when we want to do CMB lensing at wave numbers of 1,000 or so, we'll have to think very carefully about the SZ contribution, because it will bias the reconstruction. But at the moment, it's not a problem.
And what about the effect of other secondary anisotropies, like the integrated Sachs-Wolf effect? Is it in order of power of L, or does it, we have to take care of it for lensing, or?
Yeah, well, the ISW effect is...
It's very low L, right?
It's low L. Also, to do with observation, it's a Gaussian foreground. So it doesn't add any phase correlations to the CMB map, and so therefore the lensing reconstruction shouldn't pick it up.
So I'll just clear up one more confusion of mine. So when we say that, okay, dark matter only interacts with baryonic matter, let's say only gravitationally. This is true from the beginning of the universe, or because I'm thinking before reionization, baryons and dark matter are like very close. So do they still interact only gravitationally, or there should be some electromagnetic interaction? Because or is it like, okay, it will only interact gravitationally and no other thing, even when they are very close to each other at the beginning of the universe?
Well, okay, there will be some about this in the next lecture as well. But the short answer is that in the early universe, the baryons and dark matter become quite strongly separated.
They become strongly separated.
They do, because baryons can interact with each other by pressure forces, which dark matter interacts with other dark matter only by gravity. So in the early universe, when radiation pressure is high, because in the early universe, you can think of the photons and the baryons as being a single fluid that's glued together by Thomson scattering. So the radiation can't propagate through the plasma because it's always being scattered. So when the radiation pressure is high, so the radiation density is important above a redshift. The universe is radiation dominated above a redshift of about 3,000. So at that point, the baryons have a speed of sound, which is approximately the speed of light. Okay, so that redistributes the baryons relative to the dark matter on any scale up to the horizon distance. How far can the speed of light propagate at that time? Now later on, when that pressure is removed, the baryons and the dark matter can fall back together. But at late times, astrophysical effects can separate them again. So you've heard talks about galaxy formation and about the whole process of feedback. So that means that when star formation happens, massive stars go through their life cycles, supernovae are generated, and they return energy to the intergalactic medium around them, heat it up, and so gas can be expelled from dark matter halos, and the baryons and dark matter become separated on small scales again. So on scales of megaparsecs, treating the joint distribution of baryons and dark matter is very complicated, which is why you're much happier talking about these sort of scales of hundreds of megaparsecs where there can't be any significant separation.
could we go to the slides where we dissect the contributions coming from various redshifts? So after redshift 20, there was this rainbow. Yes. Now when we look at all these layers, can we say that the width of the thickest part of the width is moving to the right when we look at these plots? I'm trying to see if we can correlate this to some dominant structures at a given redshift. For example, later in the universe we have these voids, filaments, sheets. Earlier, maybe not so much. I wonder which structures mostly, bring these results or these effects.
Sorry, I'm not quite sure what you're asking. If you look at this, which is the contribution of structure within redshift 0.5, you can see it's most important at pretty low wave numbers, Aleph up to say 20 or 30. So large angular scales, but that kind of makes sense because you look at the cosmic web and it's in front of your face, so the closer it is, the bigger angle it subtends, and therefore the smaller wave numbers would be dominant. Conversely, if you look at large scale structure at extremely high redshifts, then the angle it subtends is very small and should be important at high wave numbers. And so, as you go out to progressively larger L, you can see that contributions of the lower redshift bands become unimportant. So redshift below 0.5, by the time you get to Aleph 200 or 300, it's negligible. If you could probe to L of 1,000, Mike's died, has it?
Yeah. That was not working a few seconds ago, but this is working.
Yes, it is, okay. Or I could just shout. So you can see that if you want, conversely, if you want to probe high redshifts, I don't know, between say 5 and 10, so that's this orange contribution here. It's a tiny fraction of the signal down at the lowest wave numbers, but it becomes a dominant fraction that's, I don't know, Aleph, well, it's a very substantial fraction at Aleph 500. So the higher redshift you want to probe, the higher L you need to go to. But that would be complicated then, because the large wave numbers also get contributions from the nonlinear structures at low redshift, because I showed you. Remember this thing? So here's the galaxy autopower. So you can see at L of 1,000, it starts to matter at low redshifts whether you understand the nonlinear fluctuations or not. So although probing high redshifts, small angular scales starts to become exciting, there's nonlinear challenges have to be understood.
So is this mostly due to voids, or what of these substructures lead to this, contribute the most to this difference?
Okay, well, why these nonlinearities happen is, there's a whole formalism for understanding this, which is a thing called the halo model. You've heard of this term? And really what it says, I can explain this briefly. So remember that what dark matter does is it collapses into nonlinear units, which are the halos. At high redshift, you just have some weakly perturbed distribution of dark matter. At low redshift, that becomes dark matter clumps at various sizes. Yeah. So you can ask, what is the power spectrum of these two things? Let's build up to this one. So suppose I just take a distribution of halo masses. And to start with, I'll take those dark matter halos and I'll place them at random throughout the universe. Well, the power spectrum of a random distribution is just white noise. If you put points down at random, the power spectrum is independent of scale. Let me plot this as it's dimensionless power, though, which is k cubed times the power. So we can plot k. So this would be something that, in these logarithmic units, is much more inhomogeneous on large scales. Sorry, not at large k, at small scales. We can make this more realistic. Because first of all, we can say, well, the halos are actually not points, they're objects of finite size. So that means that you need to convolve this with whatever the density of the halo is a function of radius and the halo center is. And what that does is lower the signal on small scales once you're looking at sufficiently fine scales, that is wavelengths of order of megaparsec, that are sensitive to the actual sizes of the big dark matter halos. But now you can also say, but wait, I've placed these halos at random, but they only existed because there's a spectrum of abnormal density fluctuations, and small wavelength components of that have collapsed to make the halos, but the large wavelengths are still present, so the halo centers should be moved so that they still reflect the cosmic web. And therefore, you should say, okay, on this same plot, I can ask, what does the power spectrum of linear CDM fluctuations look like? And the answer is it looks like that. So the total, no expense spared, in colour, the total, therefore, has that form. And we give these names then. So this is the two halo regime and the one halo regime. And that's exactly, that transition is what you're seeing here. Okay, so this, that point where the red pointer rests is at that breakpoint. So at large scales, we're simply seeing the correlated positions of the centers of dark matter halos. But at small scales, we need to understand their internal constitution, and that can include, whether the baryons have been redistributed as well, which is why it's a regime that you're better being to the left than to the right. Will that help?
Yes, yes.